engineering batteries for sub-zero performance. When winter temperatures drop, battery performance often drops with them. For businesses operating electric fleets, remote infrastructure, data centers, or critical backup systems, that decline is not theoretical. It translates directly into operational risk. Charging slows, available capacity shrinks, and systems designed for reliability begin to underperform. The underlying issue is well understood. Most commercial batteries rely on liquid electrolytes and rigid inorganic electrodes that are optimized for moderate climates. As temperatures fall, ion mobility decreases, electrolytes can crystallize, and electrochemical reactions slow. What appears to be a seasonal inconvenience at the consumer level becomes a continuity concern at enterprise scale. During the Midwest cold snap in 2024, electric vehicles in some areas struggled to charge, underscoring a broader point. Energy storage is now embedded in operational resilience planning. Winter performance is not a secondary specification. It is a board-level risk factor in certain sectors. Researchers at Texas A&M University are exploring an alternative approach. Their polymer-based, dual-ion battery is designed specifically to maintain function in sub-zero conditions. In laboratory testing, the system retained most of its capacity at 0 degrees Celsius and more than half at 40 degrees Celsius, while continuing to deliver high-power output. Rather than focusing solely on management systems or external heating, the work targets the materials at the core of the battery. Rethinking materials for low-temperature performance. Conventional lithium-ion batteries face compounding challenges in the cold. Liquid electrolytes that efficiently transport ions at room temperature become more viscous as temperatures fall, restricting ion flow. Simultaneously, rigid inorganic electrode materials exhibit slower electrochemical kinetics, further reducing charge and discharge performance. The Texas A&M team addressed both constraints through material substitution. Instead of a standard electrolyte, the researchers employed a diglin-based formulation engineered to remain fluid and conductive at low temperatures. On the electrode side, they replaced traditional inorganic materials with redox-active polymers, flexible compounds that maintain chemical activity and structural integrity in colder environments. By aligning electrolyte and electrode behavior for sub-zero operation, the battery avoids the internal resistance spikes typical of conventional systems in winter. For operators, this could mean less severe derating curves and improved predictability in cold weather deployments. The broader implication is strategic. Rather than compensating for cold conditions with heavier insulation, heating systems, or software workarounds, battery performance can be addressed at the chemistry level. Structural integration and system-level economics. Beyond electrochemical performance, the research also considers mechanical design. Traditional batteries incorporate metal current collectors that add weight and can degrade under vibration, load stress, or repeated thermal cycling. In transportation, aerospace, and industrial equipment, these factors influence both lifespan and maintenance cycles. In this design, carbon fiber weaves replace metal collectors. These conductive fibers serve a dual function, carrying current while reinforcing the battery structure. The result is a form of structural battery where energy storage contributes to mechanical strength rather than existing as a separate weight-adding subsystem. For sectors focused on power-to-weight optimization, such as electric mobility, drones, or robotics, this integration could support reduced overall system mass, improved durability under mechanical stress, potential simplification of component architecture. From a total cost of ownership perspective, durability and weight reduction can be as significant as incremental gains in energy density. Fewer discrete components and enhanced structural resilience may reduce maintenance demands and extend operational life in demanding environments. The technology remains at the research stage, and commercial viability will depend on scalability, manufacturability, and long-term cycling data. However, the direction is notable. As climate volatility increases, temperature resilience is becoming a primary design requirement rather than a niche specification. For utilities, telecom operators, logistics providers, and operators of remote or critical infrastructure, batteries are now load-bearing assets in both literal and strategic terms. Cold weather reliability influences uptime, service levels, and reputational risk. In the near term, thermal management remains essential. Over the longer horizon, materials innovations such as polymer-based low-temperature chemistries suggest a different path, one where batteries are engineered to tolerate extremes rather than shielded from them.